In logical terms, when discussing the relationship between an antecedent and an outcome, it's important to distinguish between necessity and causality. The antecedent can be a necessary condition for the outcome, but this doesn't imply that it causally produces the outcome. Here's a breakdown to clarify this distinction. Necessary conditions. A necessary condition is a condition that must be present for an event to occur, but by itself, it might not be sufficient to cause the event. In logic, this is often expressed through conditional statements, if-then statements. The structure of such statements highlights that if the antecedent condition is not true, then the consequent outcome cannot occur. However, the presence of the antecedent alone does not guarantee that the outcome will occur. Example: consider the statement, "If it is raining, the ground is wet." Here, rain is a necessary condition for the ground being wet because typically, without rain, the ground wouldn't be wet, assuming no other sources of water. However, rain by itself does not cause the ground to be wet if, for instance, there is a protective cover over the ground. Causality, on the other hand, implies that the presence of one event, the cause, directly produces another event, the effect. In causality, not only is the cause necessary, but it is also usually sufficient to bring about the effect under the right conditions. Example: lighting a match, cause, typically results in a flame, effect. The act of striking the match and the presence of sufficient oxygen cause the flame to ignite, illustrating a direct cause and effect relationship. Logical implication versus causality. In logical terms, implication. A logical implication does not always represent a causal relationship. For instance, if a figure is a square, then it is a rectangle. This statement is logically true because all squares are rectangles, but being a square does not cause a figure to be a rectangle. It merely fulfills the definition. Causality. In logic, causality isn't typically represented using simple conditional statements. Instead, causal relationships might be explored through causal logic or formal systems that model dynamics and interactions, like causal diagrams or Bayesian networks. Understanding this distinction helps in analyzing arguments, formulating theories, and interpreting conditions and outcomes both in theoretical contexts and in practical, real-world applications.